So let's have the solution to example 7 in two methods. One is the scalar approach, right thumb rule, and the other one is by vector approach. So the turnbuckle is tightened until the tension on the cable AB is 1.2 kilonewtons. So remember, tension is pointing away from the point of application. Calculate the magnitude of the moment about point O of the force acting on point A. So you have the freedom to put the force at A or at B. So I will put it at A, and for your case, you have to put it at B. So remember that the force in vector form is the magnitude of the force, then times quantity, components of distance. So because we have to describe the direction AB, where the force is directed to, so it is going down. So along Z is -2, so we have -2k here. Then go right. This is parallel to the y-axis, and it is in the positive direction, so that's why we have 1.5j. Then move forward. So going forward, it is 0.8. That's why we have 0.8i here, divided by distance. And the distance is simply the sum of the squares of these components of distance. So f, therefore, in vector form is 0.3657i plus 0.6857j minus 0.9143k. So we put these components at A. So along x it's positive, along y it's positive, so to the right, and along z is negative, so going down. First, for moment about OX, so position your right thumb towards the positive x-axis, then curl your four fingers. That's the direction, that's the positive moment about OX. So it should be that way. I hope you check it with your right thumb there. So that's the positive direction of moment. So automatic, the x component is ignored because it will not produce moment about a parallel axis. So we only consider the y and the z axis, the y component and the z component. But obviously the z component passes through, if you extend its line of action, it passes through the x-axis, so therefore this produces zero moment also. So what is left is the y component of force, which produces negative moment because the curling or the moment of the y component is opposite to this curling or arrow. So it is negative 0.6857 times 2 meters. That's the distance between this force and the x-axis through point O. So negative 0.6857 times 2. That's the moment about OX. The negative 1.3714 kilonewtons. Now, how about y? So position your right thumb towards the y-axis, then the positive moment would be the same as shown in the figure. So let's ignore the y component. Let's concentrate only with these two forces, the x component and the z component. For the x component, it is same sense as this, so it is the same, right? So it is the same curling. So it is positive 0.3657 times 2. For the y component, it is also positive. It is the same direction. So you have to position your right thumb towards the y-axis, and you notice that the curling of your four fingers will be the same curling as the moment of this force, positive, moment of that force, positive. So MOY is equal to 0.3657 times 2 plus 0.9143 times 1.6 momentum. So it's the same. So MOY therefore is equal to 2.1943 kilonewton meter. Finally, about Z, position your right thumb towards the positive Z direction with reference at O. Then the curling of your four fingers would be in that direction. So that's the positive moment about OZ. So automatic, this Z component is ignored because it is parallel to Z. So we consider the X component and the Y component. But the X component, when extended, passes through the Z-axis. So this produces zero moment also. Therefore, the only force that has moment about the Z-axis is the Y component of force. And the moment of this Y component of force will have the same sense as this. So positive 0.6857, the moment arm or distance is 1.6. So MOZ is 0.6857 times 1.6. So in MOZ is 1.0971 kilonewton meter. So in vector form, this is the result. So you have to copy the x, y, z components, then the units is kilonewton meter. But the question is, we have to calculate the magnitude. So the magnitude is square root of the sum of the squares of these x, y, z components of moments about point O. And its value is equal to 2.811 kilonewton meters. Next, the vector approach. So remember that moment about O is, so this is the reference. So we define a radius or position vector from O to any point on the line of action of the force. Remember the definition of moment of a force about a point. So it is ROA cross the force or ROB cross the force. So I leave to you this second way. This is ROB cross F, and I'll just present ROA cross F. The result should be the same. And try to solve this case so that you can practice. You can master moment of a force about a point by vector approach also. So next is first is the vector ROA. So let's describe OA direction. So you go up, so that's along Z, so that's 2K, then move forward, we reach point A. So this is positive 1.6 I because it is towards the positive x-axis. So therefore, the vector form of ROA, we write the components of OA in the first row, then components of force in the second row. We already have force components already. Then in the third row, we have to write the unit vectors IGK. Then we extend this just like computing matrix or determinant, rather, basket method. We copy the elements of the first two columns, you can remember. And remember also that positive is going down to the right and negative is up to the right. Remember? So let's begin with I. So we have 0 times negative 0.9143I, so it's 0. Then minus this direction, minus that direction, so this is positive, so because that's minus, so minus 0.6857 times 2, which is this minus 0.6857 times 2, so it's the same for J component. So 2.3657 times 2, can you see that? This is this first term here, minus negative 0.9143. So negative of negative 0.9143 is positive. So positive 0.9143 times 1.6. So that's why we have here 0.9143 times 1.6. So it's the same for the Y component. For the Z component, we have positive 0.6857 times 1.6, which is that. So minus, so this product is 0 because of that 0 there. So it really verifies that MOZ is the same. So therefore, in vector form, the result is the same as this. So we have the detailed calculations for moment about O. So 0 times negative 0.9143, which is that, minus 0.6857 times 2, which is that. So which is the same as this. Then for the J or Y component, 0.3657 times 2 positive minus negative, so minus negative So positive 0.9143 times 1.6. It's the same. Then along K or Z axis, so 0.6857 times 1.6 minus 0, which is the result is the same. The magnitude is the same, 2.811 kilonewton. Okay, so let's stop.